Hello everyone. I just started a new playlist for vibrations. Of course, just selected topics, not all of vibrations. And this is the first video on shock spectrum. So when we look at the behavior of structures, one of the forces that we care about are the forces with impulse behavior, the ones that have short durations and large magnitudes, like earthquake or so. And we want to look when those shock forces are happening, what is the maximum response of the system, right? Because that's the most important thing that determines the maximum stress in the system, the failures, and everything. So, the first thing is, how do we model a shock? Well, in general, the shock forces are over a short period of time, and if you look at their forces, they are not like a regular well-known function. So they happen over a short period of time with a lot of oscillations. You cannot really model it with a nice uh, like mathematical function that we learned in calculus. And so you might approximate that. And one of the approximations that is kind of similar in nature is a half sine wave. Okay, so here we have a half sine wave where f of t equals f naught sine omega t. F naught is the magnitude of the input, and t only goes between 0 to half of the period. Remember, period t is 2 pi over omega, so half of that pi over omega is half of the period where the signal extends, and after that it just becomes 0. Okay, so like for example, another example you can see is if you have a car and this car is basically driving over a bump, right? Then this could be another example. So when you pass over a bump, that bump can also be modeled by a half sine function. So we want to see what kind of maximum response you would get. So uh, if we look at the maximum response of a system to this kind of half sine wave, right, as you change the frequency of it, this plot is what we call the shock spectrum, but the question is what system? And here, for simplicity, we only use a single degree of freedom system that is undamped. So basically all it is what a mass and a spring, right? Which is subjected to this displacement, this sine wave here, right? And you want to look at this response x and find the maximum response, okay? And you assume there is no damping, so the system can have large magnitudes in general, but if you know damping, you can add it. But in general, the plot is going to be what? The maximum of x that is happening over time versus what? Versus this omega. Okay, or in general over omega n, where omega n, as you know, in vibration of a single DOF system is square root of k over m. Okay, so you plot that, that is called shock spectrum. So how do we do that? Well, here, the equation of motion is basically mx double dot plus kx or equal to negative kx plus the force, right? If we want to write it in ma equals some f, right? And then here, the force is a negative kx, the spring force, and then what? Plus the external force F, which here we show with F of t. Well, clearly this is a second order differential equation with linear coefficients, and it has a homogeneous part, right? And it has a particular part. The homogeneous part is a sustained oscillation with natural frequency as the frequency of it, and the x of particular depends on the type of this function. So here is that solution. As you can see, you can find it here by this convolution. And if you find it, this is the solution, where this part of it, as you can see, is that particular solution times that coefficient, and this other part of it is what? Is that homogeneous solution. Okay, you see the frequency of that is omega, and the frequency of that is xp. Again, in this coefficient here is it's in both of them. Okay, this coefficient is for both of them. Of course, this other one also has this extra coefficient omega over omega n. Okay, so this is what you have. Now, if you have sustained oscillation, then this x of h stays, because that's what you have here. The system is undamped. So x of h does not go to 0. Okay, it does not. But if there is a damping in the system, this x sub h will converge to 0. X sub p does not. Okay, and you have seen it in vibrations. Maybe I make one of my future videos about this single DOF force versus free response, damped versus undamped. But here I want to look more into applications. And so this is the solution you have. And you might say, where would you get this convolution from? Why would you do it with convolution? Well, that's just one way to do it. Because if you apply Laplace transform to this system, you know that the Laplace transform of this system is what? If you have x of s over f of s, then it is going to be basically 1 over ms squared plus k. Okay, so now if I have this function and multiply both sides by f of s, then I'll get what? I'll get x of s to be f of s times this what we call transfer function, correct? And so this f of s is what here? In this case, f of s is the Laplace transform of f naught sine omega t. So this f of s is going to be f naught and then over s squared plus omega squared, right? This is the Laplace of the sine function with omega t times magnitude. So you need to multiply these two things together, and then x of t, if you want, right, is going to be the convolution of this one in t domain and that one in the t domain, and this is what you have over here. Okay, right? This is for that sine term. This is the delayed version of the 1 over ms squared plus k term, and it is integrated from 0 to t. That magnitude is there, and this is your solution. Okay, so the reason is this for this convolution is the inverse Laplace. Okay, the inverse Laplace of those two functions. Okay, so this is my solution. Now, this is not what I care about. I care about the maximum of this x. Where does this x get maximum? And to do that, we use basic calculus knowledge. We take derivative of this x with respect to time, x dot of t, set it equal to 0, and see at which t it becomes maximum. We find that t, plug it back into x to get the maximum value of x. So here we take derivative of this function. That is just a constant coefficient. Derivative of sine omega t becomes cosine omega t times omega. Derivative of this guy, this omega n, will be multiplied to that, so it cancels that. So it's going to be omega cosine omega nt. So both terms will have an omega, which comes out here, as you can see. The coefficient is still there, and then you get cosine omega t minus cosine omega nt. Now this guy has to be equal to what? 0. Of course, this coefficient cannot be equal to 0, right? That cannot be equal to 0 for because this omega is non-zero, everything else is, okay? And so an f naught is not 0. So this term here, this parenthesis, has to be 0. Now the way you solve this trigonometry equation is use the equality of cosine alpha minus cosine beta equals negative 2 sine alpha plus beta over 2 sine alpha minus beta over 2. Where this guy you consider it to be alpha, and this guy you consider it to be what? Beta. So if you plug in that, then basically you'll get this. And that negative 2, when you set it equal to 0, that negative 2 can be cancelled. So it's sine of the 2 added divided by 2 times the time of the maximum is 0, or sine. And here Tm is the time at which what? At which this solution becomes maximum. So here I said T prime M, and T prime M is the final answer. But if you want to be basically following the notes, let's just call it Tm. Okay, so now you have two sine terms multiplied together equals 0 instead of two terms subtracted or added. So now it's easy. It's either the first term that is 0 or the second term. And you know, in general, when you say sine of x equals 0, x is what? X is any integer multiple of pi, like I times pi, where I is an integer number. So that's what's happening. Either omega n plus omega divided by 2 times tm is I pi, or this minus term times tm is equal to I pi. So we multiply both sides by a 2, you get 2 I pi, and then we divide either by this term or by this term, and that's what you can see. They are combined into plus and minus. You get two solutions. So there are two solutions. One of them is for with the negative is for the second term. The one with the positive is for first term. So one of these two times you call it t prime m. The other one you call t double prime m. Okay, so you have two general solutions. And it's more than two really, because for any I, these solutions will change. But these are the general form of the solution. So now I plug those t back into my x equation, which is this one over here. I plug it in, and that should give me what? That should give me two different solutions for x maximum, and that's what you can see over here. So these are the two solutions you can get for t prime and t double prime. Now, which one of them is bigger really? Let's take a look. So although this term is bigger than this one, right? Because the numerators are the same, denominator of this one is 1 plus, that is 1 minus. So denominator of this is smaller. So that ratio is bigger, that's right. But remember, it's inside the sine function. So at max, this term can be a 1. It cannot grow more than that. But if you look at this other one, here the numerators are the same, the coefficients when you look. This has the smaller denominator compared to this one. So in general, this x at t prime is the bigger one, because although this bottom one has a bigger term, but it's inside the sine function, it cannot grow too much, okay? It at best can be 1. So at t prime, the solution is generally bigger than t double prime, so we choose the top one, and this is the solution of the top one in general, where again, I here is what? 1, 2, and all the way. Okay, so this is x max, and the t that we used here is only for the time that the exciting function is applied. And remember, your exciting function is applied between what two times? Between 0 and what? Pi over omega, half cycle. So this equation, this max equation, is also only valid when t is between what? 0 and pi over omega. This is the maximum response you can possibly get. But then you might come and say, well, what about when the excitation goes away? So when f is equal to the second part, what about the maximum on that part, right? Because remember here, although the excitation, the external excitation goes away, but the homogeneous response doesn't go to 0. Remember, your solution, if you look at it, it has two parts, this one and this one. Even if this one goes away, this one doesn't. This is an undamped system. So you cannot just ignore that and say, hey, we don't care what happens after the sine wave, the half sine wave is gone. We have to look at that one as well and look at the maximum for that part as well. So this is what we do here. We use the same convolution, but this time we use for a time t, which in general can be any time. And in this case, this t is bigger than pi over omega. Okay, so here we allow it to the time to extend for after the termination of the exciting force. Okay, the half sine wave. And if you do that, again, the solution is very similar to the previous case, except there is no omega term. As I said, the omega is gone. We don't have this one, but the omega n term does exist. So you see both of these terms have omega n only in them. Okay, and again, to find the maximum of this x, again, we take a time derivative, we set it equal to 0. This time you get two cosines added equal to 0. Remember, this guy can never be 0. So it's this one, and again, we use the equality of cosine alpha plus beta equals 2 cosine alpha plus beta over 2 cosine alpha minus beta over 2. If this is equal to 0, 2 cannot be, so it's either the cosine of average or cosine of the average of the difference should be equal to 0. So it's either this one or this one is 0. And in general, remember, cosine of x, when it's 0, it means x is what? Is like I plus 1/2 times pi, where I is an integer. Okay, so it's like pi over 2, 3 pi over 2, and so on. So if you do that again here, you might say, what kind of solution would you get? Well, here, because you're after this small t, right, not after capital T, so you set this first one equal to 0, and if you do that, you find the time at which the response becomes max. So it's going to be 2i minus 1 times pi over 2 omega n plus 1/2 t, and t here is the time from 0 to t is used for evaluation of the response. Plug it back into x here, plug it back here, and you get this bottom function here. Okay, so this is the maximum when t is what? Bigger than pi over omega, when the excitation force is gone. Now, one thing we have to pay attention, so now we are going to plot. We are going to plot what in both of these cases? We are going to plot x max versus what? Versus this ratio omega n over omega, or omega over omega n. Okay, we're going to plot it versus this case, and if you look at the top one, it's similar. Look, here is a function of this ratio. So we're going to plot it for that, which is going to be basically this curve here. And this is the spectrum shock. Now, plot. Now, the thing is, where would you use the equation 1? Where would you use equation 2? Okay? So we have to pay attention to that part. And for which ranges of frequencies, right? For which ranges of omegas. And this is the thing. If you look at this equation number 2, remember this x max is the maximum value and is positive. So if that has to be positive, then this guy here cannot be negative. This subtraction term cannot be negative. That means what? That means that omega, basically n, has to be less than omega. Okay, if omega n is bigger than omega, that can be negative. So this equation 2 is good when omega is less than, omega n is less than omega, or your excitation frequency is more than natural frequency, as you can see. Okay, but if you look at equation 1, when does this x max in general can be positive? Well, if you look, this guy here should not be negative, and that is happening when omega n is bigger than omega, or omega is less than omega n. So use equation 1 when omega is what? Less than omega n. And if you combine equation 1 and 2 for those two ranges of frequencies, then you will get what? You will get this plot. So here the x-axis is omega over omega, and the y-axis is k max, k times x max divided by f naught. So the magnitude of the response of the system is normalized by the magnitude of the input multiplied by k, and you can see that term in both of them, right? You can see it in both of them, because if you look here, you can see that this f naught is here, and this k is here. So I multiplied by k and divided by f naught. So what I'm plotting is basically only this part. And similarly here again, right, if you look, you can see that, again, k is here and f naught is here. So basically I'm plotting this 2 times omega n over omega times that. So if you combine again, this is your spectrum shock. Now, the way I generated this plot is by MATLAB. So here I have my MATLAB code. where I set up an arbitrary value for m, k, and f naught. F naught I just use 1. K is 25, m is 1, so omega n clearly is going to be 5. Then I generated a range of frequencies from 0.2 omega n all the way to 10 omega n. And I use 100 values. So I'm going to run my Simulink file, in this case 100 times. Each time I grab one of the frequencies in this big W and call it a small w, which is my omega really, the omega of the sine wave. Using that, I run my Simulink file, I get the data out of it, x, record the maximum of it in this vector x max, so later I can plot x max times k over f naught versus omega over omega n. And that is this plot here. Now let me show you my Simulink file. So this is my Simulink file. And if you look here, I have a 1DOF mass spring system. This is my mass. Okay, I got it from SimEscape. So what you need to do is to go under SimEscape, right here, and then you go to Foundation Library and go to Mechanical, and then go to Translational Elements. You can find mass. If you need a damper, you can find it. You need a reference for mechanical translation, a point that does not move, a wall or something, right? So that is this guy, and you need the spring, which is this one. And when you bring the spring, you can double click on it and you can plug in what? You can plug in a value for that, okay? You can give it a K. There are other values, but we are not concerned so much about it. So that's the mass spring system attached to a fixed place. And then I bring this guy, which is called ideal force, which is gonna simulate my half sine wave. So under SimEscape, under Foundation Library, under Mechanical, you go to Mechanical Sources. And you see there is ideal force source, ideal angular velocity, ideal torque, ideal translational velocity. So I pick this one, I bring it in, and one end of it, which is S, the source, it is attached to here, to this block that is creating my half sine wave. And then I have C and R, okay? C is attached to the ground, R is attached to the motion, is attached to the mass. So it applies to the mass basically, right? And the other end is attached to the ground. So this force is basically relative to the ground. And then I need to measure the position of this block and send it out. So I go under Sensors, Mechanical, and I bring this guy called Ideal Translational Motion Sensor. That is this one. You double click here and you can measure anything you want. You can even give it initial position. So position, velocity, acceleration, whichever one you want to measure, you can check. And again, you can give your system an initial position. So here I'm good with 0, and attach one side of it to the block, attach the other side to the ground. So it's motion of the block with respect to the ground. And the output of that, P, is going to go to my scope block. Now, Simulink, SimEscape blocks, these guys, these second generation blocks, they cannot be directly attached to regular Simulink blocks, these guys. If you see these wires are black, these wires are green and brown. So the way you can use a signal generated using regular Simulink blocks for SimEscape, and the signal generated in SimEscape, read them into oscilloscope, is using these two extra blocks, right? Which you can find them here under the utilities. And one of them is called PS to Simulink converter. PS stands for physical system. So it converts your physical system, which is this guy, this mass spring system here, into a Simulink block. And the other one is this one, Simulink to physical system. So here the Simulink signal is converted into a signal that can be read into this physical system. Okay, you also always need this solver configuration block, which is also under the utilities. You connect it and you can basically set up some configurations for the numerical ODE solver. So I typically don't change it unless I have a reason to. This is good. And the way I generated a half sine wave, I brought the sine wave here. And for magnitude of it, you see I plugged in f naught, frequency of it is omega, and the sample time is 1 over 10 times omega. Okay, so I make sure that I can get at least 10 times 10 samples, right? So if you look, when my omega, because remember the period of your signal is what? The period of your signal is 2 pi over omega, or like 6.28 over omega. This is what? This is 0.1 over omega. So 0.1 and 6.8. So it's like 62, 63 samples per period. Okay, that's how many samples I can get per period. So make sure that the sample time is not a constant number, because when the frequency goes up, then if you don't sample it enough, you might not get the X max properly. Okay, so use a formula for the sample time, so as the frequency changes, your sample time also gets what? Smaller and smaller. And here, to get rid of the second part of the sine wave, I use two step functions. One goes from 0 to 1 with the same sample time. The other one goes from what? It starts at the time pi over omega. Where was pi over omega? It was the time that the signal ended. So this signal starts when the time is over and it goes to value of 1. You see again with the sampling frequency. So if I subtract these two step functions, I get a pulse. I get a pulse of 1, which is only 1 between 0 and pi over omega. Now, if you multiply it by the sine function, the result should be what? It should be a half sine wave. And if I double click on my scope, let me see. So this is the result of that. It is a half sine wave, of course, at a very large frequency. So I can probably zoom into this area. And there we go. You see, it is a half sine wave, which only extends to, in this case, pi over omega, and omega in this case is 10 times omega n, which is 50. So this number should be pi over 50. And you see, still my sample is enough that I can see the sine wave in here. If you want, you can make it smaller, but this is good enough. And all the other system parameters are also coming directly from my MATLAB code. You see M here, you see K here, so, and F naught and everything. So I'm allowed to change anything I want. The other thing is, when you go to this scope block, you want to send your data to the workspace, right? So this is the behavior of the system, and when omega is 50, and you go here under the setting and make sure you export the data, log it to the workspace. Here I call it X, and you have to use a structure. In this case, array does not work. When you use the second generation blocks, they do not support arrays, so use a structure. Okay, so I send it out as X, and if you look at my M file here, I use x.signal.values to read all of the values in the structure X. Now this X comes with 3 dimensions. It is gonna have 2 redundant dimensions. Okay, so it's gonna, instead of like 200 by 1, it's like 200 by 1 by 1. Okay, so I use the command squeeze to get rid of all those extra dimensions and just get one simple vector, get the maximum of it, and later I will plot it, which, as I told you, is this graph. And one interesting thing about this graph is, as you can see, the maximum here is happening when omega is about 0.6 times omega n. Okay, so this is not like, you might say, why didn't it happen when omega was equal to omega n, and why didn't the magnitude went to infinity? Why didn't we have a resonance, right? Because remember, when we have a system with no damping and the frequency of the harmonic input is the same as natural frequency, you will get resonance. Why didn't you get resonance, and why the resonance is not at omega equal omega n, or the ratio 1? Well, because here you only have a sine wave that is half and it does not repeat. That resonance is when this full sine wave keeps repeating itself. Here you only have one shock, and as a result of that one shock, here your X maximum does not get infinity. It's just a limited number. It's just like 1.8 basically times F naught over K. and it happens when the ratio is 0.6. Okay, so here you can see the shock spectrum for a single DOF system. And again, if you have a simple car model, you can say that this is kind of the behavior you expect when the car goes over a speed bump, right? So if I go over the speed bump, then if I know the natural frequency of the right of the car, which I'm gonna make a video about it, my next video is gonna be on car ride models. If I know the natural frequency of my car suspension system, if the frequency of the bump is about 0.6 times that, then I'll get what? I'll get the peak, probably up and down motion. So hopefully this video was useful to you. Under the video description, I'm going to share with you the Simulink and this M file, so you can generate your own plot if you want. You can change the parameters. Just pay attention that it takes a while before you get the plot, because here I'm running my Simulink 100 times, okay? So look under the video description and download these files and play with them if you want to learn more about a shock spectrum. Thank you so much. I'll see you in the next video.